Page 86. It was more than a century after Harvey had discovered the circulation of the blood that two other scientists, one English and the other French, discovered oxygen. These men saw that when a flame burns, it takes something out of the air. That is why a candle goes out when it has been burning for a little time in a small amount of air. It has taken all the oxygen out of the air. You may see this by putting a lighted candle under a glass cover. So, when the candle has used up the oxygen from the air, it cannot go on burning. It cannot burn without oxygen. Its light goes out. So with the burning that goes on inside the millions of cells of our bodies. If the blood stops carrying oxygen to the cells, they go out. They die. Page 87. When we are running, our hearts are working much harder than when we are sitting down. Our blood is being pumped more quickly through our bodies. The blood must carry a greater supply of oxygen to the muscles all over the body. Our hearts work for us automatically. A heart can pump as much as 3,000 gallons of blood a day. The amount pumped at any time is controlled automatically. After running hard, we breathe very quickly because while running, we couldn't take in enough air for our oxygen needs. We are out of breath, as we say. Page 88. Our bodies control themselves in many other ways. For example, the temperature of our bodies, and those of all warm-blooded animals, is controlled. Our blood temperature is kept at 98.6 degrees Fahrenheit, or near it. When a person is very ill, some of the automatic controls of the body stop working. The temperature, measured by a Fahrenheit thermometer, may go as high as 103 degrees Fahrenheit, or 104 degrees Fahrenheit, but if it goes much higher, or keeps as high as that for very long, one cannot go on living, but will die. Page 89. If you have a high temperature, you will feel unwell. Then it is good to go to bed and send for your doctor. You may have to go to a hospital. A nurse is taking this patient's temperature. He has had a bad cold and has been in bed for a day. He felt unwell. His temperature went up to 102 degrees Fahrenheit, but it is down again. The nurse is looking at the thermometer, which she put under the man's tongue. He has kept it there with his mouth shut for 2 minutes. The man's temperature is 98.6 degrees Fahrenheit. That temperature is right for a healthy person. Page 90. The body has many different ways of keeping itself warm enough and not too warm. It uses up more food, more fuel for the cells in cold weather. It shivers. That is, its muscles go on making quick little motions to keep it warm. We cannot stop ourselves from shivering. The body's heating system is not under our conscious control. It is automatic. To stop shivering, we have to warm ourselves some other way. We may run or walk quickly, or take hot drinks, or cover ourselves up warmly, or use hot water bottles to warm our beds. Page 91. Our bodies give off some of their heat all the time by sending a little liquid out through the skin. Sometimes the amount gets greater and our skin becomes wet. This cools the body quickly. Here the man on the left is shivering because he has been waiting in line for a long time in the cold wind. The man on the right is wet all over because he got too hot in the sun. He is drinking water because he feels the need of it. He is thirsty. Page 92. This man is in training. He is going to run a distance of 1 mile in the shortest possible time. The fastest runners before him have taken a little under 4 minutes, and he wants to make a new record. When a man runs a mile in 4 minutes, he is going at a rate of 15 miles an hour, but it is not possible to keep running at this rate very long. The runner is standing now in front of his doctor, who has an instrument in his hand. Through this, the doctor can hear the sounds made by the runner's heart. Page 93. Now the doctor is taking the man's pulse. He has his finger on the man's wrist and is counting the times his heart pumps the blood in 1 minute. The doctor can feel the motion or pulsing of the blood every time the man's heart pumps. In most people, the pulse rate is between 70 and 80 times a minute. In children, it is higher. The runner's pulse rate is 72. It will be higher when he is running. Page 94. There is a good story about the use the great Italian scientist Galileo once made of his knowledge of the pulse rate. Galileo lived 300 years ago, before people had watches for measuring time. In the 16th century, there were very few clocks in the world, and no watches. One day when Galileo was a young man of 18, he was in the great church of the city of Pisa, where he lived. Watching the motion of a light hanging down on a long chain from the roof high above his head, he saw that as the light moved forward and back on its chain, it seemed to take the same time between turns, however far it went. Page 95. To see if he was right about the motion of the light, Galileo put his fingers on his wrist. He timed the motion of the light as it went forward and back on its chain, measuring it by his pulse rate. He was right. He had the proof. He could prove that the time was the same, however short or long the journey of the light through the air was. Galileo had made a great discovery about the motion of a pendulum. Among other things, this discovery made possible a better instrument for measuring time, the pendulum clock. Page 96. Measuring how fast something is moving gives us the rate of motion. This plane has gone 300 miles in half an hour. Its rate was 600 miles per hour. This man has walked 2 miles in half an hour. He was walking at a rate of 4 miles an hour. Now he is standing. He is not moving. This man is working slowly. His pay will be small if he is paid by the amount of work he does in a day. This other man is working quickly. His pay will be high if he is paid by the amount of work done in a day. The two commonest ways of paying a worker are by the hour and by the amount of work done. Piecework is work paid by the amount done. For different sorts of work, rates of pay may be different. Sometimes rates for the same sort of work are different in different places. Page 97. In different countries, different sorts of money may be used. In the USA and Canada, people are paid in dollars. In the UK, they are paid in pounds. The rate of exchange between the USA dollar and the pound in 2004 was about $1.76 to £1. You could exchange a pound for $1.76. Here are some other rates of exchange. They are for the business week August 16th through August 20th, 2004. A table of exchange rates is printed in the newspaper. Page 98. When we move about from one country to another, we sometimes have to change our money, we sometimes have to change our watches, and sometimes we change both. When we change our watches, we move the hands forward or back, forward if we are going east, and back if we are going west. Here is a map giving timelines across the Pacific Ocean. In the days when Galileo used his pulse as a timekeeper, most people did not even know that the Earth was round. They knew no more about the journey of the Earth around the sun than they did about the journey of their bloodstream through their bodies. Page 99. But 2,000 years before Galileo, there were Egyptians and Greeks who knew more than a little about the motions of the sun and stars and the angles between them at different times. Some few Greeks even knew that the Earth is not flat, as it seems, but round like a ball. One of them even said that it was about 25,000 miles round, which it is, and that the Earth moved around the sun while turning on itself. It is from the Greek language, sometimes through Latin and French, that many of the words used in science have come. For example, Page 100. But for another 2,000 years, most people went on thinking that the Earth was flat, like a large plate with the sun and stars journeying round it. How is the idea that the Earth is not flat but round like a ball proved true in the end? Sailing men went out in their ships to find a way by water from Europe to India and China. Though some ships from the north of Europe had sailed west to parts of America in the 10th century, most of Europe had no knowledge of the land across the Atlantic. Men like Marco Polo had gone east to India and China, much of the way by land, long before Columbus in 1492 went sailing west with the idea that he could get round to the Far East by water. Page 101. Christopher Columbus has gone down in history as the man who discovered America. He was looking for a way of getting to the east by sailing west. It was hard for him to get help for this journey. He was laughed at by most people when he said he could go this way to India because the Earth was round. This is the sort of ship Columbus sailed in. He made use of a half-hour sand glass for measuring time at sea. Through all the long months, the glasses on Columbus's 3 ships had to be turned every half hour as the sand ran out. Page 102. People living in America were named Indians by Columbus because he thought he had got to India when he discovered America. He went back to Spain without knowing that he had found a new continent. He knew nothing of the life that had been going on in North and South America for thousands of years, or of the 2 great peoples, the Aztecs and the Incas, who had been living there, the one in Mexico, the other in Peru, for centuries. It is now thought that in 1500, the population of the Americas was about 30 million, and that the first of these Indians had come from Asia themselves. There may have been a land bridge between Asia and Alaska across which they could have come. Page 103. 30 years after Columbus discovered America, the ship of Magellan, a sailor of Portugal, was the first to make its way south of South America and on round the world through the Indian Ocean and past the Cape of Good Hope back to Europe. Magellan himself died on one of the Philippine Islands on April 27, 1521. When a ship sailed out to the west and came back home from the east 3 years later, people could see that the earth must be round. This proved that the earth was round. It was proof enough for most people. Page 104. But it was harder to take in the idea that the earth might be moving round the sun, as Copernicus of Poland, 1473 to 1543, said it was. Very few people had made any sense of the writings of Copernicus by the time he died in 1543, 21 years before Galileo and Shakespeare were born. Few people could read or write in those days. It was Galileo who made the first telescope, through which he could watch the stars and look into the ideas that Copernicus and others had been working upon. Through his telescope, the stars seemed more than 30 times as near, and he could see not only the mountains of the moon, but spots on the face of the sun and the motion of the moons moving round the planet Jupiter. Page 105. Galileo could let people look through his telescope, but he could not make most of them see the picture of the universe that was becoming clear in his mind. He could not do that any more than Copernicus had been able to do it. People's ideas were changing, but not as quickly as his. Galileo was put in prison for saying that the ideas written down by Ptolemy 1,500 years before did not make sense to him. Page 106. Newton, who was born the year that Galileo died, took the new line of thought much farther. Like Galileo, he became a great watcher and recorder, asking the question, how, more than why, and answering by measuring and recording and comparing and proving. Even more than Galileo, he saw the universe as part of a great machine, and he was able to put into words great natural laws, accounts of its workings. Page 107. He was able to do this only because he was carried forward on the shoulders of such men as Galileo, Kepler, and Copernicus. With their work before him, he could think out new ideas about the weights of things and their motions. His law of gravitation says that all things in the universe have an attraction for one another. It was only by standing on Newton's and other scientists' shoulders that Einstein was able to get his picture of the universe and work out new ideas about time and space and energy. Their work made it possible for him to see farther into the laws of the universe than they could. Younger scientists, in their turn, are developing new ideas made possible by Einstein. Page 108. The thinking of scientists has become clearer and truer as their instruments have become better. Galileo made one of the first microscopes as well as the first telescope, and by the middle of the 17th century, this new instrument had opened up another world, a world of things too small for our eyes by themselves to see. The microscope made possible the discovery of the cell structure of all living things. Even the human body could be pictured now as a great machine with millions upon millions of working parts, each part a cell. Page 109. Together with all this new knowledge of the cell structure of plants and animals, the microscope opened up a world of living beings so small that people had no idea such things were possible. It was a surprise to the scientist to see that in a drop of water there might be thousands of living things of many different sorts moving about and taking in food. With the invention of such instruments as the microscope and telescope, people found themselves walking between two strange new worlds, one too far off and great, the other too near and small for anyone but the scientist to know much about or do much about. As science developed, thinking people came to feel less and less at home in the universe. They had enough knowledge to be conscious of the need for more. Page 110. Our bodies can be looked upon as machines which are kept going by fuel. As food is burned up in the body cells, it gives us heat and other sorts of energy. All through our lives, from birth to death, we must be supplied with energy. Even when we are sleeping, we are using up some food to keep our bodies warm. Our lungs and heart keep on working. Some animals sleep through the cold winter weather. Snakes, for example. When they are asleep, their rate of breathing and pulse rate and temperature go down, and less food is needed. Only animals that can store enough fat in their bodies to keep them alive through the winter can sleep through the months when food is hard to get. Page 111. While our bodies are at rest, the large muscles are not in use. It is these large muscles which pull on our bones and let us move as we want to. Hard work with our large muscles uses up energy quickly, so that we come to feel hungry and want to eat. The more we know about the parts of our bodies and their work, the more new questions come to our minds. Questions such as, how is it possible for all the different parts of us to grow from one cell? How is it possible for all the millions of cells in our growing bodies to go on doing what they do without our being conscious of their workings? Page 112. Through about 2 billion years, scientists say the development of plants and animals on our Earth has been going on. At first, both were very small, much less than a pinpoint in size. We might say that the first plants or animals were bodies living in one-roomed houses, too small for the eye to see. All the housekeeping went on in one room. Such cells take food in and let waste out. They do not give birth to new cells, but divide to become two daughter cells. These three pictures show the division of a cell into two separate cells, each of which may in turn divide into two more. Page 113. The Earth itself is thought to be more than twice as old as life on it. Our picture of what it was like 2 billion years ago is of a great ball, about as hot on its surface as boiling water. In time, as the Earth's surface became less hot, the thick clouds round it, from which water went on raining down, got thinner. Then more sunlight could get through to the surface of the Earth. Sunlight is necessary for life on Earth, as air and water are. Page 114. Life began, people think, in the salt sea, near the land where the waters were not deep. Very small one-celled organisms came into being. The cells in our bodies are of many different sorts, but they all have water in them. Our bodies are 70% water. This water has in it about the same amount of salt, common table salt, as there was in the water of the sea in which the earliest organisms swam. That water was a little less salt than seawater is today. In billions of years, the rivers have washed down more and more salt from the land into the sea. The sea has become more salt. The water in our bodies does not become more salt. Even if we eat a great amount of salt in our food, the body automatically controls how much it will keep in the bloodstream. And the same is true if we let very much salt out through the skin when we get overheated. Then we have to eat something that will give us new supplies of salt. Page 115. The first living things, though they were too small to be seen, were eating, growing organisms, which divided to become others like them. Under a microscope, a cell looks like a bit of clear jelly, with a thin wall around it. Very small openings in the walls of the cell let food in and waste out. In every cell there is a part like a little ball. This is the nucleus, which organizes the work of the cell. Those cells were discovered 2.5 centuries ago. It is only in the last 100 years that knowledge of the work of the nucleus has developed. It is this nucleus which keeps the cell working at what has to be done. It is to the cell what London is to Britain, New Delhi to India, Beijing to China. It is the seat of government. Page 116. All living things are developments from these one-celled organisms. They have developed step by step, through change upon change from these first simple living things. Our bodies and the bodies of the plants and animals we see about us are highly complex in their structure. They have in them millions of cells, some doing one sort of work, some another. Every different cell has its own sort of work to do. What do the words simple and complex mean? Page 117. The greater the number of parts a thing has, the more complex it is. The smaller the number of parts a thing has, the simpler it is. Which of these is the more complex? The more different the parts of a thing are from one another, the more complex it is. The less different the parts of a thing are from one another, the less complex it is. Which of these is more complex? Page 118. The more the parts of a thing need one another, the more complex it is. Take one little wheel out of a watch, for example, and see if the other parts can do their work without it. Which is more complex? A stone or a plant? The leaves, the flower, stem, and roots of the plant work together to keep it alive, but each does a different sort of work, and each is dependent upon all the others. The work of each part is different. The parts of a stone do not work in this way for one another. A stone is a much simpler thing than a plant. Any living thing, however small or simple it may seem, is far more complex than anything which has no life. Page 119. People are the most complex of all organisms, far more complex than any plant. We would not go on living, but would die if the millions of cells in our bodies did not work together in their different ways, each doing its own sort of work. The cells are dependent upon one another, and we are dependent upon our cells. The picture below shows what the word dependent can mean. The girl in the middle is dependent on both men to keep her from falling. The man who has been holding her feet is letting go as the other man takes hold of her hands. She has been dependent on the first man. She will be dependent on the second. Their act depends on timing. Page 120. There are about 5 million red cells in 1 cubic millimeter of our blood. 1 millimeter is 1,000th part of a meter and 1/10 of a centimeter. 1 cubic centimeter. How much space does that take up? Here is a picture of a cube which is 1 centimeter long, 1 centimeter wide, and 1 centimeter high. It takes up 1 cubic centimeter of space. A centimeter is a little less than half an inch. Page 121. You can put a paper cube this size together for yourself, or cut one out of soap or cheese. To make a paper cube, take a pencil and make 6 1-centimeter squares like this. Now take your scissors and cut round the outer lines. Do not cut the broken lines, but make folds there. Put the edges together to make a hollow paper cube, as in the picture. Your cube will be a cubic centimeter in size. A cube has 6 sides. Its sides are equal squares. The surface of a 1 centimeter cube is 6 square centimeters. In 1 cubic centimeter of our blood, there are about 5 billion red cells.